Hello, you're welcome back. All right, so continue from where we stopped. Now we're going to be looking at the component of alternating current circuit. All right. So the component of alternating current circuit are basically called passive components. Why are they called passive components? Okay, they mostly serve as a load, and they do not provide amplification of the alternating current. What I mean by amplify, they don't amplify the signal, they don't increase its magnitude, all right? So they only serve as a load. Basically, unlike active components, okay? Component can be divided into passive and active. Active component actually takes in signal or alternating current, then actually uh, change the waveform of the alternating current, either by amplifying it or possibly to shape it in some way. For example, transistors are active components, okay? They can take in alternating current and then amplify it, all right? But passive components don't do that, okay? So the passive component we're going to be looking at is going to be resistor, capacitor, and inductor. So basically, these are what we are going to be using to, okay, as our alternating current circuit component. So the component of alternating current circuit will be basically be resistor, capacitor, and inductor. So we are going to be taking it one after the other, all right? So we will start with the resistor. So resistive circuit. So that's a circuit, alternating current circuit that have on the resistor, all right? Now, of course, this is the symbol of the resistor, and the parameter of a resistor is always its resistance. For capacitor, the symbol of capacitor here is what we have, and the parameter of capacitor is its capacitance, and for the inductor, the parameter of the inductor is its inductance. So I'm starting with uh, that of resistor. Okay, so this is the resistor R. Okay, then I connect an alternating current. Of course, this is the symbol of an alternating current voltage source. All right. So, and this is the resistance. So let's say what I measure, this alternating current is basically the VRMX. That's what the value. So once I supply this alternating VRMX across this resistor, then of course the current flows through it, which let me say IRMX flows through it, through this resistor. Now I told you that the opposition to the flow of alternating current is what we call impedance. Okay, so by formula now I can simply say that impedance, according to voltage, according to Ohm's law, voltage is always equal to current multiplied by resistor. Okay, but in terms of alternating current, I will simply say that the root mean square value of the alternating current is going to be equal to the root mean square value of the current, then multiplied by the opposition to the flow of alternating current, and that is the impedance. This symbol here is the symbol of impedance. Okay, opposition to the flow of alternating current. Now, so it happened that for a resistive circuit, okay, only contain resistor. So the only opposition that we get here is just the resistance. Okay, so the opposition to the flow of the alternating current is simply the resistance of the resistor. Okay, now a resistor is actually a component that doesn't actually provide reactance. The only component that provide reactance is capacitor and inductor. I'll tell you what is reactance. Okay, a resistor only provide resistance. Now reactance is simply okay, the opposition or the delay. Any component that provides reactance to an alternating current or voltage actually causes that, either causes it to probably delay, okay, or causes it to have a phase angle. Now, what I mean by delay, okay, if a current was supposed to start from the origin, then it delays. Okay, that is actually that can be only be caused by capacitor or inductor. So they are circuits that can provide, and they are components that can provide reactance. But a resistor doesn't provide reactance. So that simply means that an alternating current circuit that have only resistor will have these characteristics. Okay, this is one characteristics. I've already this one characteristics. The impedance of that particular of the impedance of the circuit will be that of resistor. Okay, so the opposition to the current will be resistance. Number two, number two characteristics is that the voltage, the voltage, okay, and the current, they don't lag. Okay, they don't lag each other. They are in the same phase. Okay, are in phase. So there's no phase angle between the voltage and the current. No one is actually lagging the other. Okay, and of course, you know what I mean by phase, being in the same phase. That simply means that if I draw uh, the graph of the current will start from the origin, so there's no phase angle. And the same thing happens with the voltage. If I draw the graph of the voltage starts from the origin. Okay, there's no phase angle. So the phase angle is zero, and the first angle of this is also zero. So there's no difference in their phase. They are in the same phase. So please take note. Anytime resistor, okay, is connected across an alternating current, both the voltage and the current and the phase. That's why I say that a resistor does not provide reactance, okay, to alternating current. Now you will see what happens if we actually connect uh, alternating current across a capacitor. Let me start with that of an inductor. Okay, so let's now look at the inductive circuit. Right, let me clean up. All right, so inductive circuit. So I will connect an inductor first. You know, an inductor is a coil. Okay, an inductor is simply a coil. So I connect alternating current across it. All right, current flows, voltage is also supplied. Okay, now the characteristics you are going to notice is that the voltage now is now leading. Okay, the voltage actually leads the current. V leaks I. Okay, and they leads it by 90 degrees, which simply means that when the current is actually at 0 degree, the voltage is already at 90 degrees. Okay, in the circular motion. And of course, 90 degrees is something as pi all over 2. So if I should write, or let me draw the graph of the current. Let's say the current starts from the origin. If I'm drawing the current starting from the origin, okay, then this is a graph of the current. Then that of the voltage will start from 90 degrees to show you that the voltage is leading the current by 90. So that is why I can say that the phase angle is actually 90 degrees. Okay, so If I should write the equation of this current here, simply the current is going to be equal to I equal to the maximum current then sine omega t. But if I'm writing the equation of the voltage, this voltage with time, okay? The equation of the voltage now will have a phase angle in it. So that's going to be V is equal to Vm, then sine open bracket omega t, okay? Then plus the phase angle, and that phase angle is 90 degrees, okay? But I won't use 90 degrees. I have to convert the 90 degrees to radius. 90 degrees to radius is always pi all over 2 radius, okay? So that's going to be pi divided by 2. So that means the voltage is always leading the current by 90 degrees. If it's actually an inductive circuit. So now that simply means that the inductor actually provides what is known as, okay, the opposition that the inductor provides. This is one. So that's we simply mean the impedance now of the circuit, okay, will now be equal to the impedance that the circuit, the opposition the circuit provide now becomes the what? The reactance of the inductor. Let me just, okay, let me write that by symbol. The impedance becomes reactance of the inductor. So the opposition to the total opposition that is offered by the to the flow of alternating current is actually due to the reactance of the inductor. Okay, of course we use Z. Z is impedance. So the impedance becomes the inductive reactance. The symbol for inductive reactance is actually SL. Okay, so XL represents inductive reactance. All right. So now the question is, how do we actually calculate the inductive reactance? Formula for inductive reactance, if you want to calculate the opposition to the flow of alternating current, okay, by the inductor, known as inductive reactance, is given by the formula omega L. Of course, you know what omega is. Omega is is angular frequency, right? Is angular frequency. You know, you should know that, okay? In wave, omega is angular frequency. Okay, angular frequency. And do you know, okay, that angular frequency is equal to 2 pi f? So that way I can simply say that the inductive reactance is given by the formula 2 pi, 2 pi, 2 pi f, then multiply by L. 2 pi f multiplied by L, okay? So let's say, for example, this circuit now have an inductor of inductance 0.001 Henry. The SI unit of inductance is Henry, okay? So let me write that down. Let's say we have an inductance of 0.001 Henry, okay? In alternating current, whose frequency is equal to 60 Hertz. 60 Hertz. So we are now asked to evaluate the inductive reactance. Simple. That's going to be 2 times pi. Pi is 3.14 multiplied by the frequency 60 multiplied by the inductive reactance 0.01. Okay, and of course your answer, the SI unit of your answer is in what? In ohms, because it's an opposition. Okay, anything called opposition to the flow of current is measured in ohms, be it resistance, all right, be it reactance, they are all measured in ohms, or even be it impedance, all of them they are measured in ohms. So I hope that is well understood. Okay. Now let's now move and see how. Okay, let's look at the last component, which of course is that of a capacitor, capacitive reactance. So look at a capacitive circuit. So of course we connect the capacitor across the voltage supply source, alternating voltage supply source. Okay, the capacitance is C. Now the characteristics you should know this time around that it is the current that's leading. Okay, the current actually leads the voltage. Current leads V. Let me just, okay. I leads V, of course, by 90 degrees. On the other way around, you can simply say that instead I say I leads V by 90 degrees, or I will say that V lag, okay? V is lagging behind, lags I by 90 degrees. So V is lagging this time around. Remember, in that of inductor, V was leading. So here V is lagging. For example, if it happens that, let's say my alternating current start from the origin, okay? Okay, if my alternating current start from the, that means the the voltage, all right, will be 90 degrees, will be at negative 90 degrees, okay? Will go this way, will lag the current by 90 degrees. So you see where I started, okay? At minus 90. So that simply means that if I'm writing this for voltage, okay, so if I should write the equation of the current, okay, it should be maximum current, then sine omega t, no phase angle, okay? That means phase angle is 0. But if I'm writing the for that of voltage, voltage is going to be equal to Vm, okay? Then the sine of bracket open omega t, then that's a lag. So that's going to be minus 90 degrees, okay? Of course, 90 degrees in radians is pi all over 2. So I hope that is well understood, okay? So that's number one characteristic. Now, number two characteristic is the fact that the impedance now, the opposition, the total opposition to the flow of the alternating current is going to be purely, okay, capacitive reactance. Capacitive reactance. Okay. So the question is, how do we evaluate capacitive reactance? Okay, of course, Z is the impedance. So the impedance is going to be equal to the capacitive reactance. Okay, so that this XC here is what we call capacitive reactance. Okay, reactance of the capacitor. So SC by formula is given as 1 all over omega c. Already we know that omega is 2 pi f, right? So S is going to be equal to 1 all over 2 pi fc. Okay, so let's look at a situation where the capacitance is, let's say, 2 microfarad. So that means the reactance of the capacitor now, let's say for an AC circuit whose frequency is 50 hertz. So that's going to be equal to 1 all over 2 times 3.14 multiplied by the 50 hertz, then multiplied by 2 times 10 raised to the power of, that's 2 microfarad, right? 10 raised to the power of minus 6. So I believe you can do this. Use calculator and do this, and you have your capacitive reactance, and it's measured also in ohms. Okay, ohms. Okay, so I hope that is well understood. All right, so now let's now look at the combination of the three components. The combination of capacitor, inductor, resistor. Okay, capacitor, inductor, and resistor. Okay, so let's draw the circuit. Oh, please pardon me. Okay, so let me use this, okay, this symbol for resistor. Okay, so this is C, this is L, and this is R. So once you have this now, okay, you discover that there will be reactance, okay, and there will be resistance. So I can combine this into what is, combine all the relationship, okay, of the voltage, the impedance, okay, in a simple diagram, right? Remember, C always voltage, okay, of C always lag behind the voltage of L by 90 degrees, okay? While for R, both the voltage and the current, okay, are in the same phase. There's no lag. So if I should draw the vector diagram, okay, that vector diagram, we also call it vector of phasor. Okay, remember we talked about, okay, phasor diagram of the voltage of this particular component. So look at how we draw it. For resistor, there is no phase, so I will use horizontal line. Resistor, there's no phase between the voltage and the current, so that will now be represented by horizontal line. Now, for an inductor, the voltage also is leading. The voltage is leading the current, so I use a vertical line, okay? Remember, and it's leading by 90 degrees. So this 90, okay? So let me, this phasor diagram, the phasor diagram I'm drawing is the phasor diagram of voltage, okay? Of voltage. So as I said, for resistor, there is no lag. So I use a horizontal line. So that's going to be VR. This for resistor. But for an inductor, okay, the voltage leads the current by 90 degrees. So that would be a vertical line. So that's going to be VL. But for a capacitor, the voltage lags the current by 90 degrees. So that will be coming down, okay? Negative. That's be moving in the negative downward. So let me use a different color. All right. So this one is VC, voltage across the capacitor. Okay. So this is how the voltage across the inductor, resistor, and the capacitor are related in a vector or phasor diagram. So now it is the combination of the voltage across. Remember, what I deliver, what the circuit deliver is actually VRMX, root mean square value, okay? So it is this VRMS that is actually shared between that of capacitor VC, okay, that of an inductor VL, okay, and that of a resistor VR. So which simply means that the combination of all these, okay, the addition or the resultant of these three voltages, what will give me the VRMS of the circuit. So the question is, how do you sum a vector? How do you sum vector? Okay, I'm sure that you know how to sum vectors. If you want to sum vectors, this vector, okay, if you want to find the resultant of this vector, simple. You know how we do that, okay? We use Pythagoras rule because I have vertical and horizontal, okay? For you to sum vertical and horizontal vectors and okay, for you to sum vertical and horizontal vectors, you know very well that you apply Pythagoras rule, okay? So of course, the resultant of these vectors, let me not call it, remember the resultant of this vector, their voltage, okay? The resultant of this voltage is what we know as the VRMX of the circuit. So how do I do that? Okay, so I'll start with the horizontal. That will be VR square, then plus the vertical. Now it happened that I have two opposite vertical. One is acting upward and one is acting downward. Okay, so of course you know in vectors when two vectors are acting in opposite direction. Okay, for you to get the resultant, you subtract. So that what I'm gonna have is VL, all right, minus VC, then all square. All right. So let's say if, the voltage across this resistor is across the capacitor is 10 volts. The one across the inductor is 20 volts, and the one across the resistor, the voltage across the resistor, let's say is 10 volts. And you're being asked to find the RMX value of this circuit. Simple. So the VRMS value is going to be equal to voltage of the resistor 10 square, bracket open, voltage of the inductor is 20, 20, then minus 10, all square. So this is gonna give me 100. Of course, 10 by 20 minus 10, that's also 10 square, that's 100. So at the end of the day, I'll have the square root of 200, okay? So you can use calculator to do that. That is the VRMX. Now the question now, this is the total voltage for the three component: capacitor, inductor, and resistor. What of their impedance? Okay, So it's very important for me to get the impedance. So what now happened to the impedance? Yes, I will resolve the impedance the same way. Okay, so still based on the impedance, I will still draw the phasor diagram. So the phasor diagram is still going to be similar to what I drew before. Of course, the inductive reactance is vertical. The capacitive reactance is okay. Is vertical. No, please pardon me. The inductive reactance is vertical upward. Okay, positive y direction. While the capacitive reactance is still vertical but downward. Okay, then the resistance. This one doesn't have any reactance, just resistance is horizontal. So that means the impedance now is going to be the sum or the resultant of these three resistance, these three, you know, reactance, and of course that of the resistance. So I'm having R square, then plus XL minus XC, okay, all square. So it's very simple, as simple as that. Okay, so we are going to apply all this formula, okay, and it will make more sense if you apply them. So, and I will do that in the next video. Okay, so see you in the next video. Thank you very much.